Hi everyone, welcome to the presentation. I'm Ke from Purdue University, and today I'm going to share our work with SynchronizAR. On this work, I collaborated with my colleagues Tianyi, Luis, Anna, Yuanzhi, and my advisor, Dr. Karthik Ramani. The emerging mobile technologies allow AR applications to become pervasive. SynchronizAR is a registration technique to enable multiple user collaborations in mobile augmented reality. Here we demonstrate our approach in enabling spontaneous collaborations. At first, two players, Tianyi and Luis, they are playing an AR game. Then a third person, Anna, wants to join in. Our approach only requires Anna and Luis to move within a small local region for a short time. And after that, the registration is done, and the collaborative game continues with three players. Let's first examine the desired mobility here. The SLAM-based tracking brings the AR device self-localization capabilities with respect to the environment, so that with SLAM, users can freely experience the mobile AR while they are even moving around. Different from a single-user application, a collaborative co-located environment requires synchronizing multiple spatial frames across different users. A global shared frame can be established with external tracking devices. For SLAM-based AR, sharing a pre-scanned map is commonly used. However, both of these approaches are less flexible across different environments. For example, the environment may not have the external tracking infrastructure, or for a new environment, we need to rescan the SLAM map. SynchronizAR provides an indirect registration. Our approach does not rely on external tracking system so that the user can freely enjoy the mobile AR. Unlike the cloud-based AR synchronization, we also do not require any existing maps. So our approach provides more flexibility against the dynamic environment. Also, we provide better privacy control as the maps may involve some sensitive information. More importantly, not all mobile AR devices have the same hardware and also the software SDKs. For example, the SLAM map created by AR Core may be incompatible with the ARKit or HoloLens SDKs. Our approach supports more compatibility against the different hardware and also softwares. AR has been introduced for both remote and co-located environments. Since we cannot guarantee the consistency between the local and the remote physical environments, the shared virtual contents are either spatially disconnected from the physical environment, or they only stay loosely connected with the environment. As for the co-located collaborations, common spatial references are crucial for coordinations and collaborations. To register multiple users within a global frame, external tracking devices has been used in previous works. Or by referring to a commonly shared fiducial marker, they have been, the transformation between users can be resolved. When it comes to SLAM-based AR, multiple users can actually share a pre-scanned map as their reference. So when it comes to, moreover, there are also a collaborative SLAM which allows for multiple persons to actually create the SLAM map in real time. But to do so, they have to ask the multiple agents to visit a common scene. In our work, since we do not rely on the sharing existing map, and we do not rely on the common anchors to be visited, we allow for better spontaneous collaborations. Peer-to-peer tracking and localization allows for instant registrations between users. It is attractive to directly use the SLAM embedded camera to track the pose of the collaborator. However, unless using a fiducial marker, it is still challenging to actually segment and estimate the full pose of the handheld AR device or the head-mounted device. Other direct tracking alternatives, such as electromagnetic or acoustic sensing, usually involve a bulky base. So that prevents it being used in these mobile AR devices. In contrast, the indirect approaches resolve the localization problem by measuring distances or the angle of arrivals between different nodes. Early works from Hazard utilized ultrasonic sensing to derive 2D locations of the stationary devices. And our previous work from this SIGCHI introduced ultra-wide bandwidth distance sensing, and we are capable of delivering IoT devices resolution with respect to a SLAM AR device. So in our previous work, we mainly focused on localizing multiple stationary nodes relative to a dynamic node, which is the user. And in this work, we resolved the resolution problem across different dynamic nodes. That means multiple users. We measure the distances between two users while they are moving around. Then we formulate a distance-based optimization to resolve the rigid transformations between two coordinate systems. Let's take a look at the 6DoF resolution between two users. As we are not sharing the SLAM map, the device A and B have two separate coordinate systems, namely F1 and F2 respectively. Then the problem becomes, given the local positions of X and Y, and also the distance measurements from the UWB measurements, how to find the rigid body transformation between F1 and F2, namely the rotation matrix R and translation vector T. Essentially, we minimize the mismatches between the estimated distances and also the measured distances across all the samples. Our unknown transformation has 6DoF, namely three translational and 3 rotational. However, with a closer look at the SLAM system, we can reduce the rotation degree freedom down to 1. The modern SLAM implementations usually involve the built-in IMU, which is the inertial measurement unit. Then the coordinate system of the SLAM map is actually aligned with the gravity. With such observation, we only need to consider the rotation angle theta about the y-axis. Further, we introduce a heuristic to reduce the translational dimensions. First, we observe a simple fact that the movement along y-axis is actually limited because of the ergonomic factors. Comparing with the movements on the horizontal plane, the y-axis movement is actually small. So we set our heuristic as follows. The user initializes the SLAM roughly at the same height. Then we, during the registration, we ask the user to kindly roughly hold the device at about the same height. Then we add boundaries to the translational dimensions for the optimization. Finally, we derive our cost function and the constraints. Up until now, we offer an instant registration for spontaneous collaborations between two users. How about for multiple users? For example, 3 users. We need to resolve 3 rigid body transformations. However, only 2 of them are independent. We formulate the 2 optimization problems separately, and then we can resolve the independent ones first. Then we derive the 3rd one, as shown in the formula. So basically, we develop a self-contained UWB module and attached on an AR device, which is a Google Tango phone here. All of the devices are actually connected through Wi-Fi, and through the UWB network, the distance are measured and packaged to one of the microcontrollers. Then the measurements will be sent to the AR devices through UWB, through the UDP Wi-Fi communication. For the AR collaboration activities, we also introduce WebRTC for rich contents. In our prototype, we utilize a remote PC for solving the optimization. However, it is totally unnecessary because any modern mobile devices should be able to handle this simple optimization easily. Overall, for the distance measurement, we reach an update rate of about 8.1 Hertz, and 100 samples takes less than 15 seconds to finish. And also, the optimization solving actually takes less than 0.15 seconds. User carry the mobile AR devices and move on independent paths. Then we feed the captured positions and distances to the solver. With the resolved transformations between SLAM devices, we established a co-located collaborative AR environment. As in this video, we are actually showing a spatial-aware video sharing application with our approaches. As you can see, two users are actually sharing a spatially aware view between each other. Primarily, we consider a two-user registration case for our technical evaluation. We started the sample parameters such as the sampling spaces and the distances between users. Our approach emphasizes on enabling the spontaneous collaborations without sharing SLAM maps. Thus, we mainly compare our result with the registration given a pre-scanned map. So, first, we capture 3,000 samples in a constant sampling volume. Then, for each test trial, we actually generate synthetic ground truth transformations from the registration. Then, for different test conditions, we draw 100 samples about 10 times. For each test trial, we actually calculate the root mean square distances for translation and theta against ground truth values. And we use these ones as our accuracy metrics. From the test, we concluded some practical guidelines for using our approach. So when the users are initializing the SLAM device, we ask them to kindly hold at about 1.5 meter. And during the registration, we ask them to hold at a constant height roughly, which is from 1.2 meter to 1.8 meter. Then we ask the user to capture at least 100 samples, and also we ask them to cover enough sampling space, which is the length and width is larger than 1.6 meter. Also, the distance is better to be at least 4 meter between users. We actually achieved the average translation accuracy about 1.15 meter, and the rotational accuracy is about 7.4 meter. To further evaluate the registration, we actually carried out the task evaluation. Again, we compared with the pre-scanned map-based registration. First, we tested the orientation reference use case. So basically, users are indicated with AR contents, and they are asked to point at different directions. From a top view camera, we actually capture the results. And for the second setup, we asked the users to do trace following. So basically, we give several different AR guidance through the mobile phone. Then, sorry, yeah. So basically, as you can see, here is the result. For the view pointing, we observe an overall mean error of about 3.7 degree, and the standard deviation is about 9 degree. And it is comparable with the suggested viewfinder frustum FOV, which is about 8 degree. For the trace following, we utilized a Hausdorff distances between the paths, and we use this distance as our metric for similarities. And then we observed that there is no significant difference between the baseline and the runtime results. Then we show more use cases using our AR registration approaches. So basically here we are showing a constructing AR game experience for the users. One user first creates AR games in the physical world, then after the registration, he can instantly share the game map to another person. And after the sharing, the second user can play the game instantly. In a co-located collaborative context, two users who are far from each other, they may also want to share views. And after the spatial registration, we can actually stitch two separately scanned models together as a spatially coherent virtual model. Then these users can actually refer to each other's shared view with spatial references. In the future, we also envision that humans and robots, they can actually communicate and interact with each other naturally. We can coordinate the robot with respect to the user's position and orientation. For example, in this use case, we ask the robot is actually mimicking the human's movement and also adjusting the orientation accordingly. So there are several limitations and the future we are targeting at. First of all, to improve the accuracy, we want to further evaluate the distance measurements quality. For example, we want to get rid of the non-line of sight inaccurate measurements. Although the Google Tango is actually providing a robust SLAM, we still observe some drift. So to fully evaluate our parameters, we want to introduce Vicon system. For multiple users, we first need to increase the update rate of the measurements, and also we want to carry out an overall optimization approach for the non-independent transformations. And for the AR devices form factors, as we are not relying on the SLAM maps, actually we support more than just the handheld devices. The head-mounted devices such as HoloLens and all different other hardwares can be utilized also. So also we want to thank all the constructive suggestions from the reviewers, and also this work has been supported by NSF. I will take questions now. Thank you.
Thank you very much for questions. Please step up to the microphone. While there might or might not be a question, I actually have one or two. Diego, go ahead.
Hello, I'm Diego Martinez from Sussex. I really like the job. It's really nice. But just came to my mind, you're saying that the accuracy might be a problem. Right now you're using the distances between each of the peers together with your SLAM reconstruction to compute the transformation matrix from one to the other. The thing is that you could know more. Like, I know where I am in my SLAM, but I also know where I am relative to the origin of my world. So when you're broadcasting, you could be broadcasting where I am and the direction in which I'm moving. That way, if I know that the distance has changed from D1 to D2, I also know that that decrease in distance has happened in this local direction to the other user. You've got a lot more information there. Did you?
Yeah, that's actually an interesting thought. Right now we are more focusing on a very indirect approach, which is basically only using the distance measurements and the local coordinates of separate coordinate systems and do a optimization. What you are suggesting,
you let the other one know what is your local position. That gives you a lot more information.
That actually, so if they start at roughly at the same position and they share some they share some common thing, then the map can be registrations through the computer vision approach directly. But I am not very sure about the direction you are referring to. We can discuss offline.
Okay, maybe it's like pen and paper. But anyways, it's really nice.
Okay, thank you.
Okay, let's thank our speakers.